Hi, 12. These videos are going to cover the rest of the functions chapter that we've been looking at so far at home. This is in tandem with the partial fractions work you've been doing with me in the class, so we can get this finished off before the end of the school year. So we're looking at inverse functions now. Okay, we've got a few more bits left of functions to look at. This is the next part. So I've got three examples of functions drawn as these kind of like mapping bubbles. The domain's on the left and the function maps from left to right. And we're looking for what the inverse function is and whether or not it exists, what the conditions are for these things actually existing. So if f maps from left to right, okay, so I'll put that on like this, so f goes that way, then for this first example, we can easily construct the inverse that reverses the function and goes back again. So f inverse, which you write this way, goes that way again. So for this first one, you can talk about what goes where. So x goes to b, if you follow the arrows, y goes to c, z goes to a. Then we can reverse the function that sends a back to z, and b back to x, and c back to y. Okay, so there's nothing here that particularly goes wrong. You can construct it just by reversing the arrows, okay, by untangling and sending it back again. Right, for these other examples though, there's things that don't quite make it work, okay, that you can't construct an inverse in this case, and you might want to think about why before I get to it. So for the second example, it's many to one, okay, you'll notice, so x and z on the domain both map to a. So if this is many to one, that causes a problem. Because if we want to construct an inverse function backwards, the question is, where's a going to go? Is a going to get sent back to x, or is it going to be sent back to z? And because you've got that choice, that excludes it from being a function. Because remember, every element of the input needs to be sent to a single output. So here's the problem. What's the inverse under a? So in this case, f inverse doesn't exist. Similarly, for this one, this function isn't onto because you've got this c down here that isn't the image of any of these inputs over here. So this one's not onto. So again, when you construct the inverse, where would c go? Because you haven't defined it going forwards. It's not an output, so it can't be an input on the way back. Okay, so two potential problems there. So the way to so the conditions then for having an inverse function is that it's got to be one-to-one, and it's also got to be onto, and that avoids both of these problems. Okay, f inverse exists when f is one-to-one and onto. Right. What you can do though, if you've got two functions like this, you can avoid this problem by excluding members of either side. Okay, you can delete things, and that's going to stop these problems from occurring. So if you think about this second example, if you were to delete z entirely, that would also delete this arrow here. So what's left over is a perfectly decent one-to-one onto function, because x goes to a, y goes to b. You can easily reverse that back again. And then for this third one, sorry, if you delete c out of this side, which is what we call the codomain, then this becomes the range. Well, that already was the range, but because that's all of the options that you've got now, you can reverse them back again. So a can go back to x, b can go back to y. So by cutting things out, it looks like we can create an inverse function by design. Okay, right. Right, so how do we find the inverse function, and what does it look like graphically? Okay, there's the other two questions that we need to look at. So hopefully this isn't kind of new stuff for you, but we'll go back through it again. All right, so it looks like a bit of changing of the subject can figure out what the inverse function is. So I'm going to get the annotation as well. Okay, so starting with 2x plus 1, just by reversing the steps, if it's an easy enough function, you can figure out the inverse quite easily. You have to subtract 1 and divide by 2. That's going to do those steps in reverse. We've talked about why a function has to be one-to-one for an inverse to exist, because if it was many-to-one, then we saw going backwards it would be one-to-many, but it's not a function. this is another way of showing you how to find the inverse. Okay, so you rearrange the subject and then you replace some labeling, right? So normally x gets sent to y. F minus 1 would send y back to x, but we don't write y as an input, we write it as an output. So you swap the labeling over, you put x over here, and you send it to a y over here. So you change the labeling just so it looks like that with x instead. Okay, a couple of examples of finding the inverse. So starting with f of x equals 3 minus 4x, you can replace f of x with y because that's convenient for when you want to change the subject. Then you make x the subject of your equation, so x equals 3 minus y over 4, and then you change the labeling, so rather than y it's sent back to x, and rather than y it's f inverse of x. Okay, so you change the labeling at the end. For these ones it's a little bit trickier, but you can still do it by expanding and factorising. Okay, so you start with y equals, and then you multiply up, expand, collect, and then change the letters and put back again. Okay, so back to this again. And you might want to spend some time looking at what the steps are just to make sure you can do those ones. Okay, graphically then, what happens when you plot an inverse function is the coordinates switch around. So if, for example, on your original function, you've got 2 being sent to 5, then on your inverse function, you're going to have 5 being sent back to 2. Okay, because outputs get sent back to inputs again. So by doing that, the kind of graphical implication is that it's going to change the axes over, and it will reflect in y equals x. So that's the kind of geometric interpretation. The inverse is the reflection in that line there. In the same way, because axes are swapping over, domains become ranges, and vice versa. Ranges become domains, okay, on each of these functions. So looking at the functions, the red function is f of x. Its domain is x bigger than 1. Okay. The range of f inverse, right, the possible outputs for f inverse is y is bigger than 1. Okay, or f inverse of x is bigger than 1. So these things are swapped around. Okay, if you look at the range of the ranges as well, they're going to be the same. So the range of f, let's put that on. Give me a second. The range of f is, well, from minus infinity to infinity, so that's all the real line, and the domain of the inverse. So what can go into the blue? Well, it looks like anything can go into the blue. Okay, there's no restriction on x, so it's the real line as well. So these things basically swap over. Okay, the range of one is the domain of the other. All right, last little point I want to make. There's only a couple of examples there that you can look at yourself. If you plot a function graphically, then sometimes you can determine its inverse and sometimes you can't. So if I plot y equals, let's do a linear, shall we? Let's do 2x plus 3. There's my linear graph. It's one-to-one and onto because it passes the horizontal line test. Okay, horizontal lines hit once. There's nothing stopping me plotting the inverse if I do x minus 3 all divided by 2. Okay, that's just a straightforward plotting of the inverse. Okay, and if you plot y equals x as well, you can see the reflection as well. Right, so that's just straightforward. Okay, so most functions you can reflect and plot, but sometimes you can't. So I'm going to show you an example where this doesn't quite work. I'm going to keep y equals x, but then I'm going to do y equals x squared. Okay, right. Now, y equals x squared is a problem because it's many to one. Yep, you know that because if you plot y equals 4, this horizontal line hits twice. There's 2 different inputs for that single output. So when I reflect all of this function in the y equals x, it's going to look like this. So y equals, it's going to be plus minus, I hope that's going to work, square root of x. Let's have a look. Not sure I can get that. I'm going to do both pieces. So y equals minus square root of x. There we go. So by doing piecewise, it you can kind of see what the problem is as well. So the black reflects to this parabola here, but this parabola is one-to-many, isn't it? Because if I pick a single input, like 4, then there's multiple outputs, which isn't allowed. Okay, so to avoid this problem, we can do what we did with our mappings at the very beginning and exclude some values from our domain and codomain. So if we go back to what we started with, we started with just x squared, so let's go back to that one. What I can do is I can exclude values. If I delete the left-hand piece from here, if I delete all negative values, if I get rid of this, then that stops my function being many to 1. Because now any vertical line is going to hit just once rather than twice. So that bit's gone. Then if I reflect, then I only get this positive piece. So this is just the positive square root of x, like that. Okay, so that stops the problem there. Okay, and then when we do inverse trig functions, you'll notice that we have to do that quite a lot. Okay, it's quite difficult to define an inverse trig function because of the repetition of all the values. So that's kind of the basic idea. Okay, you can exclude things. So there you go. So let's just talk about domain and range then. So if we have f for this part and f inverse for this part, so the domain of f, the values that go in, we're going to count 0 and anything bigger. So x is at least 0. Then what's the range of the inverse, the square root of x, or the things that can come out are positive or 0. So f inverse of x is greater than or equal to 0, so they're the same as we'd expect. And then, let's just do the other ones. Range of f is positive again, so f of x is positive or 0, and the domain of f inverse, so what values can go into the square root of x? Only non-negative values of x. Okay, so again, these are the same, so as we expect, they're the same and they're the same, just as an example. Okay, that's inverse functions. For the other examples that you've got on Dr. Frost, it's just basically doing some changing of the subject, doing some sketching, doing some plotting, and working at domains and ranges. I might do one of them. Okay, so if g of x is root x minus 2, there's your domain, so real numbers 2 and bigger. So the range, the things that can come out of this, well, the output of a square root is anything that's non-negative. So f of x, well, it should say g, shouldn't it? That should say g. Change that. So g of x would be not negative. The inverse, well, I can do that by writing this down. So y rather than g of x. Then make x a subject, square both sides. Then add 2. And change labeling, so y equals x squared plus 2, and then change your labeling again. Okay, from y to inverse of f. So there you go, that's that second one done. Oh. There we go. So then sketch the graphs. You can plot them on Desmos, but you can see that they're going to be reflections of each other in y equals x. So there's x squared plus 2, okay, parabola up from 2, and there's a square root function that grows slowly. Then state the domain and range of the inverse. Well, you can reverse the domain and range of the blue one, but it's just going to be what you can see on the picture. So the domain is x bigger than or equal to 0, there's possible x's, and the outputs are greater than or equal to 2, and done. That's just the kind of thing that you should be able to do. All right, there's inverse functions covered. Any other questions on it, let me know, and that's the end of the video. Thank you very much.